All right, the first thing they start talking about are resistors. Sometimes we need to put a resistor in a circuit for different effects on the circuit. And we've talked about resistance as that kind of force or aspect that tends to impede current flow. So you might wonder, why would we put it into a circuit on purpose? But there's certainly reasons that we do, and we'll take a look at some of those.
As previously we talked about conductors, semiconductors, and insulators, and we said some substances are better insulators than conductors and vice versa. So every element has these coefficients of expansion. So for a given rise in temperature, they expand a certain amount according to that coefficient. Coefficient of reactivity, coefficient of a lot of different things. One of them is a coefficient of resistivity. So things like copper has a low coefficient of resistivity, so the resistance of copper is low. But there's other things to consider when you're looking at the resistance of a particular thing. Besides the resistivity coefficient that's inherent to the material, and you can see as we adjust the resistivity that the resistance of this piece of copper or whatever it is changes. Now the resistivity is lowering. For a given length, the resistivity changes. So if I have a section that's a ½ inch and it has a certain resistance, say 10 ohms, if it's 1 inch, it's got twice the length, it's going to have twice the resistance. So you can see here that as the length goes up, so does the resistance, and if the length goes down, the resistance goes down. The area also affects the resistance. If we increase the area, the resistance goes down because we have a bigger area for the electrons to flow through. It's like trying to run through a small culvert as opposed to a tunnel. The bigger area you have to get through, the easier it is to travel. So all three of these things, all three of these variables, the resistivity coefficient, the length, and the area, all are factors in changing the resistance of a particular resistor.
When you have a piece of any substance, it has certain coefficients. When we talked maybe about coefficients of expansion, you've got a piece of material, and when you heat it up 1 degree Celsius, it expands a certain amount of centimeters. And it varies among different substances, that coefficient of expansion. But there's also other coefficients, oxidation, there's coefficients friction, but the coefficient of resistance is a set characteristic of different elements. And if you have a substance like a piece of wire, whatever that wire is made out of affects its resistance from end to end. And the longer that piece of wire is, obviously that's going to increase the resistance as well. And the other aspect is the circular diameter, the cross-sectional area. The bigger around a substance is, or a conductor, then the lower its resistance. So in this particular case, this is a resistor. This is a large resistor. And it's a long piece of wire that's coiled round, just so that it can get a long piece of wire in a smaller space. And this is one end on this terminal, and the other end is on this terminal. So from this end of the wire to this end of the wire, there's a certain resistance. In this case, it's 40 ohms. This is a 40 ohm resistance. The reason that it's 40 ohms is because of whatever substance this is and that coefficient of resistivity, how long this substance is, and how big around it is. So those three things make this 40 ohms. Now this particular resistor is called a variable resistor. And that's because it has this additional connection called a tap. and it can move along this conductor and kind of intercept it along the way. If I have this from end to end, it's 40 ohms, and I were to put this right in the middle. Now, if I read with an ohm meter from end to end, I'll read 40 ohms. But if I read with that ohm meter from here to here, I'm only going to read 20. And I'll also read 20 from here to here, right? And if I set this at 25%, then from here to here, it's a 40 ohm resistor, so I have it set now 25% of the way up. Then how much am I going to read from here to here? 10. And from here to here? Okay, so that's how variable resistors work. Resistor ratings, the actual ohm ratings are color-coded, and that's something that I'm not expecting you to learn or memorize because there's so many charts available to do that. But there's also power ratings. If you try to run too much current to too small of a resistor, the resistor will burn up. So the ratings you need to be concerned about the most are actually the ohm resist ratings and the power ratings. But also there's this issue of tolerance, because when you have something like a 1K resistor, that 1K is nominal. That means it can, we call it 1K, but it's like you call a 2x4 a 2x4, but if you actually measure it, it's not. Or 3/4 inch pipe, that's its nominal size, that's what we name it, but if you actually measure it, it's not. And so we have a 1K resistor, but if you measure it, it may not be. It may be plus or minus. And so that's the tolerance. How much plus or minus away from its nominal rating is it? And anytime you make anything, in that manufacturing process, you can't get every piece to be exactly the same. There's always going to be variance whenever you do that. And it gets to be a question of how much can you take. In some applications, you need really, really tight controls. So you don't want the deviation from your standard to move very much. Other cases, you can be a little more sloppy, and it's not going to really affect the overall use of that particular item. And the same thing holds true with resistors. For a lot of applications, plus or minus 20% is fine. It's good enough. And you can make resistors with a 20% tolerance a lot cheaper than if you have to make them like at 0.1% tolerance. So most applications don't call for that level of accuracy, so you don't pay for that extra dollar and extra machining. But so it gets down to pick the right thing for the job. This showing some different types. Those have wires that are actually wound inside of the resistor. Some of them are just films, just carbon films, little strips. That's a different package there that you would use on an IC board. Some fixed resistors, the symbol, and some general illustrations. Variable resistor, much like the one I have here. Notice the symbol has that arrow. Anytime you see a schematic with an arrow through it like that, that means that it's variable. So you may see a power supply with that through it. It means it's a variable power supply. This is a variable resistor, a little bit, instead of being linear like the one I showed you up front here, these are rotational. And you see some smaller examples. These are what they use for like volume knobs on radios or in dimmer switches. It's still a variable resistor. And the way that it works, if you take a look there, you've got the terminals on it, A, W, and C. A and C are the ends of that piece of material, that resistive element they call it. And whatever resistance it is from A to C is based again on its size and what it's made out of. But W, this wiper, can slide across that and tap at any point in that travel, just like we did with the slide one up here. So it's the same thing in a rotational setup instead of linear. Any questions? Okay. Okay, so here we have a situation. This is a dimmer circuit, like what might be your dash lights in your car. And the current's leaving the positive terminal of the battery, goes through the fuse, the switch is closed, it enters what we would be saying is the blue one at the bottom. That was A, right? So it's going into A. We've got, as you can see in that illustration, we've got W and C tied together. So as it starts to go up around towards C, it never gets there because that section between W and C are bypassed and it comes directly down. Now, in this application, doing these lights, you tell me if I rotate that wiper clockwise, what happens to the brightness of the light? It gets dimmer. The answer is it gets dimmer. That's right. And that's kind of counterintuitive because a lot of our variable resistors are set up that as you turn it clockwise, it gets more volume or more heat or more. So as this one's wired up, it actually works backwards. If I want to make it work the other way, I just tie A and W together and leave C alone. Here I'm using the same device, but in a different way. Rather than actually limiting the current, because obviously if I'm changing the resistance in a circuit, that causes me to change the current that can flow in the circuit. And by controlling the current that's flowing in the circuit, that causes the load to work more or less. But here, instead of controlling current, I'm creating different voltages as that voltage is divided. Now, we're going to talk more about voltage division here in a little bit, but just understand that this is more to get a particular voltage than it is to get a particular current. Like I say, we'll examine the voltage division in more detail in just a little bit. So here's the color code. You've got 4-band, you've got 5-band, you've got 6-band configurations. Let's just work with 4-band in this particular example. The first stripe, and you see how colors correspond with numbers. So if I have, in this example here, I've got a red, blue, orange, silver. The first number, red, means 2. If you look at that first column there, first digit, red means 2. So the first number for this value is 2, the nominal value. The next stripe is blue, so that means 6. So I've got 26. But the third stripe in a 4-band color code is a multiplier. And in the case of orange, it is 1,000. Or you see that the number is 3, 10 to the third. It's 1,000. So the first stripe's a number. The second stripe's the second number, and the third stripe is a multiplier. So this was 26 times 1,000. The silver stripe, the last stripe, shows the tolerance, plus or minus 10%. So this is a 26,000 ohm or 26K ohm resistor with plus or minus 10%. So there's the 5-band, and I didn't put the 6-band up here. Resistors in series. So now we're starting to review characteristics of series circuits. And this is important because when you get into real applications, your circuits are going to be series, parallel, or combinations, and you need to know and understand those characteristics so that you can effectively troubleshoot. Or if you're doing an installation, so that you don't get confused and wire something up that was in series instead of parallel. I had a buddy that was a contractor, and he wired up lights in his house along a wall, and he wired them up in series instead of parallel. And so they weren't as bright as they were supposed to be because they had to share the voltage among them. And besides that, it was like old Christmas tree lights. If one bulb went out, they all went out. So it's good to understand what's going on here. So resistors in series are it's easy to calculate the total circuit resistance when they're in series because the total circuit resistance is simply the sum of all the elements in series. So our total is the sum of R1, R2, and R3. So in this case, that's 1600, right? 1.6K. Okay, everybody good with that? All right. Okay, so the voltage divider. One of the characteristics of a series circuit is that the voltage, the source voltage for that circuit is divided proportionally among all the elements or all the loads or all the resistors, however you want to think about it. And think about it maybe like this. If I've got a 100-pound weight and I'm sitting it on a 2x4, all of that weight is distributed again among all the things that are bearing it. In that case, it's just one 2x4. If I take two 2x4s, that weight is distributed proportionally, in this case 50-50, among two 2x4s. But if I have a 2x4 and a 4x4 and I put a 100-pound weight on it, the 4x4 is actually taking more of that load. So the forces are distributed proportionally. So that's what they're doing here. And we're using this for our advantage. Let's just take a look. So let me explain why we're using it to our advantage. A lot of times we have a single voltage supply, but our loads that we want to operate on different voltages than that. So if we can divide the voltage up, then I can tap off of those different parts and have separate voltages for different loads. And maybe this example will show that. So the total resistance is 10K because it's the sum of all of those. You should see that. So what's the resistance across here? All right, so because it's proportional, I have to know what proportion is that resistance out of all of it. So in this case, the proportionality, or the fraction, or the ratio, however you want to look at it, they're all the same thing. The fraction, ratio, proportionality. In this case, that resistor is 3K out of a total of 10K. So 3 out of 10. It's 3/10. That means it gets 3/10 of the total voltage. 7.2 volts. So you see that equation there. We're taking R1 and putting it over R2 to give us the ratio or decimal or fraction. And then we multiply that fraction or decimal by the total voltage, and that's how we get the voltage. Now think about this. The next resistor down is 6K. Now 6K, as far as a factor, how does it relate to a 3K? So it's double. So the 6K is double. Now what do you expect to see in the voltage, knowing that voltages are divided proportionally? What's that? It's twice the voltage of the first one. Okay, 14.4 is your answer, and that's right. Now, for the final one, we can do the same process and say, well, that's 1 out of 10, so 1/10, so that's going to be 2.4. Or we might say that, well, you know what, since the total voltage is divided up among all of the others, I can take the first two and subtract them from the total, and whoever what's left is there across that one. So this is kind of an important thing for you to wrap your head around. So I'm going to encourage you to review this, to make sure you understand how that voltage divider works. And to go back to my example of how this works for us, if I've got a 24-volt power supply, say in my computer, but the fan runs on 2.4 volts, I would design my resistors in such a way that I would get the voltage I needed. If I needed 3 volts instead of 2.4, well, then I would have put a different size resistor there. But this is there by design so that I can have the desired voltages, multiple desired voltages from a single source. And this is not uncommon to run into. All right, now we're looking at resistors in parallel. A little bit different because total resistance, just for a second, going back to series resistors, whenever I add a resistor, whenever I combine the resistances, it's always going to be larger than the largest resistor. So whenever I combine resistors in series, the number I get is always going to be larger than the largest resistor in there. Now that should just make common sense. But I'm saying that because it doesn't happen with parallel. So with parallel resistances, I've got a 60 here and a 40 here, but it is not 100. So how do we come up with that? Well, one method, it only works when you have two. Whenever I'm trying to combine two only in parallel, I use the product over sum. So the product would be 60 times 40, and the sum would be 60 plus 40. And if I plug those numbers in, I get 24 ohms. Now, when you combine them in series, the number is always higher than the highest one. When you combine them in parallel, the number is always lower than the lowest one. So our lowest one was 40, but when you combine them together, we're actually getting less resistance for that circuit. So as I add resistors in parallel, the total resistance is going down for the circuit. Questions about that? So that seems to most people counterintuitive as well. I could be adding resistors and the resistance is going down for the circuit. So then you have to start thinking about inverse relationships, like hot and cold and light and dark. So as I have a room and the hotness is going up, what's happening to the coldness of that room? Goes down. If I have a room and the brightness of the room is going up, what's happening at the same time to the darkness? Yeah, so inverse relationships work in that if one's going up, its opposite has to be going down. So the same thing happens with substances. Yes, they have a resistivity coefficient, but all resistors can conduct, and all conductors have a certain amount of resistance. So even though I'm resisting with an element, I'm also conducting. It's passing current. So I want to use this analogy. Maybe this will help. Let's say that I'm a battery, a 6-volt battery, and I'm going to move electrons. And I've got like a hallway. I've got my hallway here. And at the end of the hallway, there's an open window, and the whole hallway is filled with ping pong balls, electrons. And I've got a big sheet of plywood, and I'm going to push those electrons through the resistance, which is that window. Okay, so I've got a certain amount of push. I've got a certain amount of opposition from that window, and I'm pushing, and based on how much I can push and how much can flow, a certain amount will flow. That's Ohm's law. But if I open up another door with another window, which is another resistance, but it's also another path for conduction, and I'm going to be able to move more, right? So when I'm putting them end to end to end in a series, and I have to go through all of them, yeah, adding them, this makes it harder. But when I open up another pathway for them to travel, like in a parallel circuit, that makes it easier. And that's why the total resistance goes down. Now, if I have more than two in parallel, I can't use product over sum. And for those of you who like fractions, you're going to love this. That's how you figure out the total resistance of a circuit when they're in parallel. Now, this whole thing about 1 over a number is how you express an inverse relationship. So if I were going to say light and dark or inverse relationships, I would say that L, light, is equal to 1 over D. That tells me that L is the opposite of D. And it works both ways, hot and cold. That's how you would express that relationship mathematically. And so all of those ones there, if you look at R total, look at the bottom, the denominator, I've got 1 over R1. So I'm looking at the conductance of R1, the inverse of the resistance of R1, plus I can combine the conductances. I just can't combine the resistances. So I'm going to combine the conductance of R2 expressed as R over R1, and I'm going to add to that the conductance of R3. Now all three of those added together gives me the total conductance of that circuit, but I want the total resistance, so I've got to take the inverse of that, and that's why all of that is under a 1. So if that seems a little, well, here's a little tip. If you learn how to use your scientific calculator with how to use the inverse function, you just punch it in, but something you have to practice with. And I suggest you do, because when we get into frequencies and periods of waveforms, those are other inverse relationships. So practice using the inverse function. It'll be 1 over x, or it may be x to the minus 1. Practice using that key so that you can do it. So here's something. 2, what's the inverse of 2? What's the inverse of 2? Anybody tell me? Huh? No, but that's not a bad guess. He said -2. The inverse is simply going to be 1 over 2. 1 over 2. So if you were to put into your calculator 2, and then you hit the 1 over x key and hit that, you would get 0.5. That's how you can tell if you're using that key properly, that function properly. So the inverse of 2 is 1/2. All right, so here's a 150 in parallel with 150. Okay, so here's the special rule. Here I have 3 in parallel. I can't use product over sum because there's more than 2. I can use that method that we just went through with doing the conductances, the inverse of conductances, but anytime that you have resistors in parallel that are the same value, there's an easier way to do it, and that is to take the resistance of 1 and divide it by how many you have. So in this case, what would be the total resistance of this parallel network? 50, good, 50. All right, now current division. In a series circuit, and this is parallel, in a series circuit, the same current that flows through one resistor or element or load has to flow through all the other ones that are connected, because they're connected end to end to end. If current's entering one, it's just like pipes. I can have several pipes or pieces of tubing, and I don't care how big around they are. If they're hooked end to end to end, whatever current goes through the first one, the same amount goes through the other one, because there's nowhere else to go. It just has to be. Now, how much can flow through is probably limited the most by the smallest one, but whatever's going through there has to go through all of them. In a parallel circuit, the current divides. So in a series circuit, the current's the same in all of them, but the voltage divides. But in a parallel circuit, the voltage is the same across all of the elements, but the current divides. So here I've got a couple resistors in parallel. One's 200 and one's 400. Where is the most of the current going to flow? Through the 200 or the 400? Yeah, because a 200 is
200.
less resistance. It's offering less opposition to current flow. Do you know how much more? 2 times. Okay, good, good. So here you're solving problems that involve math, but you're not using calculators. You're just using what you already know, and it's intuition or common sense or whatever, and that's good. That's real good. So yeah, and my relationship here, um, basically I have 3 parts, so it's going to divide into 10 amps one way and 20 amps the other. And there you have the equations for that. So, well, I guess, okay, yeah, so the examples, the whole example's shown there. Questions about any of this so far? All right. This, Ohm's law again, you've probably seen this more than once, but it's just a little review. Look at it when you want. More Ohm's law stuff. Some people on the test kind of messed up on this stuff. So make sure you have a handle on what's pushing, what's holding back, and what's actually moving. All right, so prefixes. This is up here, although in my mind, this wasn't all that clear. I'm just saying, get familiar with the base units however you best do that, whether you Google it, whether you use this, whether you use the text that's provided. Whatever way works best for you is the method you ought to adopt to know how you go from base units to the SI prefixes. All right, so the idea with the SI prefixes again is we don't really want to express something with decimal points and long spaces. So if I were going to convert this to milliamps, I know that a milliamp an amp is larger than a milliamp. So I'm going to have more milliamps than amps. To get the same quantity, I'm going to do that. So in this case, I would move the decimal point 3 places to the right. And here I'm going the other way. So how many kilo ohms is that?
47.
47. 6 places because we're at mega, a million. 1/millionth. Micro is 1/millionth of a base unit. So again, make sure that you've got a handle on those things. This is all kind of review, so I'm not going to spend a lot of time on this. You should be able to do these. Some people use this. I don't know if you've seen this before, but if what you do is you take your finger, or in this case, maybe a hat, and you would cover up the variable that's unknown that you're trying to find. So if you were trying to find voltage, you would cover voltage up and you would be left with I times R. But if I'm trying to find current, I would cover I and then see that it's V over R. So that's the linear relationship expressed in this little cheat thing. power ratings. You guys did pretty good with these on the test, actually. But again, we're just reviewing that. And if you have trouble with exponents, make sure that you can operate your calculator and practice on things that you know, like 2 squared, make sure you get 4. I mean, you know, make sure when you punch the keys that you think that should be punched, that you get the answer you're expecting. This is just showing a linear relationship. It is a linear equation. Basically you see that if R, the red line is going diagonally, if it's kept constant at 10 ohms, then as the voltage goes up, so does the current. All right, series circuit. Single path for electron flow, like I said. Whatever current flows through one, flows through them all. So total voltage will be 100 volts, right? And you'll see that that was divided proportionally. Here we're looking at a voltage divider, looking at different reference points. And this is the same thing as with your lab where you're changing the meter leads, because remember that voltage is the difference between 2 points. One point serves as a reference and you're comparing the other point to it. So typically your black lead is your reference point and your red lead's comparing that point, the difference in potential to the black lead. If you take, we'll talk more about this in another chapter, but whenever you have voltages in series, the total voltage is additive. It's still additive, but they're opposing. So you wouldn't do this on purpose very often. If you wanted 6 volts, you would just use a 6-volt source to begin with. But sometimes you have things that are producing voltage that it tends to oppose the voltage you're trying to impose. And so that's how that works. It's additive, but you have to also consider polarity. All right, so what they're doing here is got a problem. You've got an open circuit. What do you expect to read? First of all, what's going to be the total current? That was a 12 ohm resistor and it's burned open or broke open. Somehow it's an open circuit. So you've got a 4 ohm and a 12 ohm. What's going to be the total current flowing in that circuit? Anybody?
4.
4?
4
How'd you come up with that?
12 times 4 over 12 plus 4.
Well, that works for parallel resistors, but these are series because they're end to end. So the key differentiating feature between a series and a parallel is a parallel circuit will have points, branch points where current can split, and series circuits lack those forks and those branches. So this is a series circuit. Does anybody have a different answer? 15? How'd you come up with that? 12 plus 4 is the total resistance of that circuit, but how much current's flowing? Huh? 0? How'd you figure that? It's open. It's an open circuit. There's no current can flow. That's like the drawbridge being up, rode out, open switch. Yeah, there's no current flowing. So right now, how much current's flowing through R1 in this table? 0. How much in R2? 0. How much total? 0. So we fill in there. Okay, so what about the voltage across R2? How much voltage is across that resistor? It would not be 24. So R, or V, voltage, is equal to I times R. We know what R is 4 ohms. What's I?
0.
0. So 0 times 4, 0. There's no voltage that can be developed because there's no current flowing. That's like if I put a stick in a stream, but there's no water flowing, then my stick won't have a force built on it to move it. So without any current flowing, the resistance there is 0. Now, I've got my next case, R1 is open. How much voltage is across that?
24.
24, but you might say, but there's no current flowing, so what the hell? There's not any current flowing, but the resistance is infinite. So you got one of these. The current? It's not going anywhere. It's really not even going up. It's not moving at all. It can't move at all because it's just like if you have bumper to bumper cars and a drawbridge is up, it's not like the car clear on the end can move. It's backed up all the way. And so are those electrons. From that open point all the way back to the battery on both sides of the open, it's bumper to bumper electrons, and they can't move until there's a pathway to move. But there is a voltage across it because voltage is the difference between 2 points, and on one side of that open, I've got the full 24 volts, and on the other side, I've got nothing, the other side of the battery. So the difference between all of it pushing and none of it pushing is all of it, the difference between that. So in an open circuit like that, you're going to see the source voltage across the open circuit. Now I've got a short circuit. So what's the total circuit resistance? First of all, is this series or parallel? Series, because there's no branching points. Don't get confused by the shape or the drawing. Look for the branching points. Okay, so what's the total resistance of this circuit? 6,000, 6 kilo ohms, right, because 14 is bypassed. There's nothing, it's out of the circuit because it's bypassed. Yeah, good? All right. So the current that's going to be flowing through this is going to be how many amps? Think about how you calculate amps and think about the total resistance, total voltage. It's pretty much straightforward Ohm's law.
1 milliamp?
No, but you're close. Should be 10. 10 milliamps. 60 divided by 6,000. By the way, when we talk about in a series circuit, the voltage is divided proportionally. In a parallel circuit, the current is dividing inversely proportionally. That means the smaller resistor, in a series circuit, when the voltage is divided proportionally, the larger resistor always gets the larger the voltage. But in a parallel circuit, when the current's dividing inversely proportional, that means that the larger resistor is getting the lesser amount of current because it offers more resistance. That should make sense. So, you know, think that through, wrap your head around it till it makes sense to you. Obviously, whatever current is leaving the source, it gets split, but then it rejoins, the two paths rejoin each other coming back out. Voltages in parallel is the same voltage because everything in parallel has the same voltage across it. The ends of it are connected to the same point, so there's no way that you could have different voltages across any of those branches. So I'll let you guys practice these on your own rather than try to work through them all. However, if you have problems with these, so that's why I say it's really better if you guys go through this stuff before you come to the class so that you already have a heads up of what I'm going to be talking about. And you've already maybe made a stab at trying to work some of this stuff out, and I can help you get across that threshold. So hopefully you've done that, but I'm not hearing a lot of questions. But in any event, if you're trying to work these and by next week you're still having trouble, make sure that you bring those up because we'll always allow some time to do that, to go over stuff. So there was a lot of them in here to try. And like I say, if you download the PowerPoint slides and just run them as a slideshow, you'll have time to work these out instead of just the answers being there already. And it's kind of good that they give you some problems that might be real life. Like you've got 3 loads here in parallel, one of them's open. How do you know? I mean, you can't necessarily see that open circuit. You'll have to be able to see it using test equipment like a multimeter. And by taking measurements and filling in these tables, either in your head or on paper, then you can figure out what's going on. All right, so here I've got a circuit. Let me ask you this. With that switch being open, how does that affect the current flowing in R3? You say it doesn't? It's kind of hard. I got these on. Okay, it doesn't because the current can leave the battery and go right through it to the other end and get back to the other side of the battery. That switch only serves to turn whatever R1 is, whether it's a light or a heater, that turns that on. So anytime this thing's plugged in, R3 and R2 are operating, and R1 only operates when I close the switch. So that circuit breaker won't trip because that switch is open. Now, if I close that switch and that's shorted, I've got a direct connection from the negative side of that battery through the circuit breaker, through the switch, to a short that goes directly to the other side of the battery. That short circuit should take out that circuit breaker. That's what it's there for. So these are some scenarios. I put these in here. These are a lot like what's going to be on test. These are actual test questions. I pulled off some of my tests. So kind of work through those. I've got two loads. These are hooked in. How are these hooked? Are these series or parallel? They're series. If you wire up your range and your washer like this, not good. For one thing, these are both. Oh, well, let me ask you this. How many volts are across the range? If I were to take my meter and read the voltage where that range is plugged in, what am I going to read?
480.
How much? 480? I will not. Because these are in series, the voltage is divided proportionally. Now, what is the proportionality between these two? Well, it's 50-50. So 50% of the voltage will be across the range, and the other 50% will be across the washer. What's I don't exactly know what would happen, but it's probably not going to give you the performance that you wanted. If it's a 240, oh, if it's a 120, that might be bad. Yeah, yeah. But just wiring something in series like this is not a good idea, because if you unplug the washer, the range won't work either. So here's a situation. This is probably coming off, maybe this is some sort of an HVAC unit. How many volts are across the pump?
500.
Should be able to see that right away. Should have answered that by now.
It's 500.
It's 500. Why?
Because in parallel, they both get the full voltage.
Because in parallel, and you guys can't hear him either, can you? So in parallel, and I'll try to work on that. So actually I came in here and the projector didn't work and it threw off my whole plan. But so yeah, in a parallel circuit, all of the devices have the same voltage across them, because the pump is hooked directly to the 500, and so is the fan. It's got a wire coming out of it, and it goes over to the 500. Here I've got a couple speakers, and the voltage is going to divide proportionally. I'll let you guys figure that stuff out on your own. And again, if you come back next week and say, I couldn't figure that out, I'll help you through it. Unless you've got an answer right now. What's the voltage across R2?
Should be 10 volts. So, no, R2 should be 20.
What are you guys saying back here? So I can tell if they got the right answer or not. You guys don't know. What are you guys saying? Which one has 10? R1 has 10 and R2 has 20. Okay, everybody agrees. Virtual and real. Real people and you guys. Okay, good. Now here I've got current dividing. Where's most of the current going to go? To the projector or the monitor?
The monitor will get twice as much.
The monitor will get twice as much. Tell me why.
Because you divide it proportionately based on the resistance.
I did not, but that's you're just off a hair. For current, I divided inversely proportional. Now think about it. One of those devices is offering twice as much opposition to current flow as the other. And that's the ohms rating. So you're going to have twice as much current flowing through the projector because it offers only half of the resistance to that current flow. Make sense? Okay. That's just it's a common mistake when you think more about the math than going with your gut feeling by just looking and say, well, wait a minute, one of those lets current through it a lot more than the other one, and you can tell that by the resistance rating. So it doesn't make sense that it's going to have more current flowing through it because it's offering less resistance. This is an amp hour. This is one of those problems we talked about, like how long is this battery going to last? We talked about that before, right? Okay. All right, so that's that. Any questions?